Imagine standing just miles away as thousands of pounds of liquid fuel and oxygen ignite. You might feel the rumble in your chest before you even hear it, and from where you're standing, the plumes of smoke may stretch across the entire horizon. It looks like power, and it looks like progress, but the reality is that in traditional launch systems, all of the hardware you see, worth tens of millions of dollars, is thrown away after every single launch. It burns up, sinks in the ocean, and is never seen again. Reusable spaceflight aims to solve this entirely. The launch looks identical, and the power feels the same. The difference is we land it, recover it, and fly it again. Today, I will be covering three things: the history of reusable spaceflight, how these vehicles control themselves during flight, and how anything survives the process of re-entering the Earth's atmosphere. So let's jettison our fairings and take off into our first point. Shortly after the moon landings in the 1960s, NASA started asking a simple but important question: what if we stopped throwing everything away? This line of thinking gave way to the world's first partially reusable space launch system, the Space Shuttle. Comprised of two solid rocket boosters, an inner orange cryogenic fuel tank, and the iconic orbiter itself. Shortly after liftoff, the solid rocket boosters would separate from the main launch vehicle and fall back down into the Atlantic Ocean for recovery. At the end of every space shuttle mission, the orbiter itself would glide back down and land on a runway like a plane. According to the Bulletin of Atomic Scientists, the space shuttle program cost around $8 billion to develop. Compared to the Apollo program's $51 billion, this is a drastic reduction. However, $8 billion is still a lot of money, so clearly something more drastic and efficient was needed. That moment came on December 21st, 2015, when SpaceX landed a Falcon 9 booster upright for the first time ever. This was a genuine, historic moment. According to NASA's NAVCOM estimates, each Falcon 9 mission cost between $60 to $70 million. The Falcon 9 paved a way for a reality where space wasn't limited to programs who had nearly unlimited budgets. As we near the point of maximum aerodynamic pressure, otherwise called max Q, you may begin to wonder how these vehicles control themselves during flight. The answer for that is something called thrust vector control. The American Society of Mechanical Engineers has a great explanation for this flight control system. Essentially, when a rocket engine gimbals, its component of thrust separates into two separate components, where the X component rotates the rocket along its center of mass, which steers the nose. In layman's terms, when a rocket engine rotates, the rocket rotates with it. This form of flight control has many benefits over other types, whereas it works in any portion of flight, just as well as it does in the lower atmosphere as it does in the vacuum of space. I'll take a moment and appreciate the view, because in a few moments, it'll be hurtling back down in the Earth's atmosphere at over 1,000 feet per second. According to NASA's publication on the aerodynamic heating of atmospheric entry vehicles, entering the Earth's atmosphere generates so much friction that it causes superheated plasma to form around the entirety of the vehicle, hot enough to destroy any unprotected hardware. Some uncrewed rockets perform an entry burn prior to hitting thick atmosphere to avoid the worst of the heating. However, the forces associated with such a maneuver are far too violent for any crewed mission. The answer for a human crew is a heat shield. Ablative or unablative, the heat shield either wicks away the superheated plasma from the rest of the capsule, taking the heat with it, or absorbs and radiates it back into the Earth's atmosphere, allowing the atmosphere to do the work of slowing the capsule down. As the ground approaches closer, we have covered three things: the history of reusable spaceflight, how these vehicles control themselves during flight, and how anything survives the process of re-entry. Our engines fire one last time, and we approach a spot we just started. We approach the stop. Our engines fire one last time, and we come back to where we started. The same rocket will be recovered, refurbished, refueled, and on the launch pad again in the coming months. If you come on by, you may be able to watch the same rocket launch again. As you make your way out, please be sure to not touch the heat shield, as it may still be hot. Thank you.